Welcome, everyone. This explainer was brought to you by Forge College. Okay, so today we're officially putting on our detective hats. We're going to be stress testing our Solidity from Zero capstone project. Now, if you recall from our last lesson, the one on library strategies and integration, we successfully wired up all those external helper libraries to our smart contract. We organized the code, we felt pretty great about it. But before we go ahead and assemble the entire final capstone contract, we really need to make sure that foundation is absolutely rock solid. So we're going to actively try to break it. We want to find the cracks and patch them up for good.
Ah, yes, the dreaded div by zero. I mean, if you're a developer, honestly, just seeing those words pop up in a terminal is enough to send a shiver right down your spine. In the world of smart contract debugging, an error message like this is essentially a chalk outline left at our code's crime scene. It's terrifying for sure, but it's also a really vital clue. And today, we're going to learn exactly how to dust for prints and solve the mystery behind terrifying errors, just like this one.
So, here is our blueprint for today's explainer. We'll start with welcoming you to the sandbox, then go over the 4 steps: reproduce, isolate, fix, and verify. After that, we'll look at case A, the fake admin, dive into some math errors and edge cases, file the ultimate debug report, and finally wrap up with preventing future bugs. Okay, let's dive into this.
Section 1. Welcome to the sandbox, our testing environment.
To get started, we essentially create a deliberately fragile contract right in our local environment. It's kind of like a house of cards just waiting for a breeze. And inside this sandbox, our absolute best forensic tool is something called instrumentation. Now think of instrumentation like spraying luminol at a crime scene. It helps you see footprints that are otherwise completely invisible. See, when a transaction fails, it doesn't always tell you exactly where it failed. So by temporarily injecting custom events, or say highly specific revert messages into our code, like inserting a quick console log or a custom debug uint event, we're basically forcing the contract to leave a glowing trail of breadcrumbs right up to the exact line of code that caused the whole thing to crash.
Moving on to Section 2. Reproduce, isolate, fix, verify. The 4 core steps.
All right, so now that our tools are ready, we need a solid methodology. Because let's be real, you can't just stare at a broken contract and hope it fixes itself. So here's the strict 4-stroke loop we're going to repeat for every single case. Step 1, reproduce deterministically. Listen, this is the single most valuable asset in debugging. If you can't make the bug happen exactly the same way twice using controlled inputs, you really can't fix it. Step 2, isolate layer boundaries. You got to figure out exactly which component is actually failing. Step 3, fix minimally. Don't go rewriting the whole contract, just patch the specific hole. And finally, step 4, verify via regression. You have to prove that your fix actually worked. So let's apply this loop to our first real case.
Section 3. Case A, the fake admin, a classic modifier bypass.
Okay, let's crack open our first case file. During our sandbox testing, an unauthorized user somehow slipped right past our only admin modifier and managed to withdraw funds. The big question is, how? We really need to isolate the boundary of the failure here. Now, what's really interesting about this slide is figuring out where exactly things went wrong. Is the bug inside the modifier, which is essentially our security checkpoint, or is it inside the function body, the vault itself? Well, in case A, the vault was actually perfectly secure, but the bouncer at the door was referencing a completely blank guest list. Why? Because of a deployment error where the admin was accidentally set to the 0 address. So the modifier itself wasn't inherently broken, but its foundation was completely missing.
So to fix this minimally, we don't need to go and rewrite our entire withdrawal logic. We just need to harden the deployment process itself by simply adding a require statement right inside our contract's constructor, which basically ensures that the admin passed in during deployment is never, ever the 0 address. We guarantee that this specific bypass can never happen again. The foundation is fixed. The bouncer now has a very strict rule to follow before the contract even goes live.
Section 4. Math errors and library edge cases.
All right, so that takes care of access control. But what about all those external helpers we integrated previously? Welcome to Case B, the universe destroyer. So we outsourced our division logic to a library called libnormalize, which features a safe divide function. But what actually happens when an outsourced calculator explodes? Like, what if a user passes a divisor of 0 into our compute and withdraw function? Well, the library throws that terrifying div by 0 revert we were looking at earlier, and boom, the entire transaction just crashes.
Now, when we isolate this bug, we realize we basically have 2 distinct ways to fix it. Option 1 is to validate precall. This means we can just add a require statement right in our main contract to check that the divisor is strictly greater than 0 before we even bother calling the library. Option 2 is to adjust the library semantics. Basically, if we actually control the library code, we could rewrite its internal math rules to handle zeros differently, like maybe returning a 0 instead of completely reverting, depending on what our business logic dictates. But usually, precall validation is going to be your safest and clearest minimal fix.
Let's take a quick second to summarize all our case files. As you can see, we solved the admin bypass by hardening the constructor. We solved the divide by 0 error by validating our inputs before calling the library. But take a look at that third row. Case C, the missing pennies. In Solidity, division doesn't do decimals. It just truncates. So if you divide 3 by 2, you don't get 1.5, you just get 1. This rounding mismatch can actually leave users with insufficient funds because they're missing tiny fractions of a token. The fix strategy here isn't just a simple line of code, it's a semantic decision. You as the developer have to actually decide whether to round up, round down, or enforce strict minimum thresholds. And then you have to write tests to ensure that your specific behavior holds true.
Section 5. The Ultimate Debug Report. Documenting our findings.
Okay, so you've implemented all the fixes. Awesome. But look, no detective's investigation is truly complete without filing the final paperwork. A professional debug report is basically your ultimate solved case dossier, and it should always contain these 5 elements. First, exact reproduction steps like how can another dev actually trigger this bug? Second, the root cause diagnosis. What was genuinely failing under the hood? Third, a summary of the code diff, basically the changes you made. Fourth, the exact terminal commands needed to verify the fix. And finally, the output traces that prove without a doubt that the transaction now succeeds. When you hand this report over to your team, you aren't just saying, hey, I fixed it. You are providing undeniable, reproducible proof.
Section 6. Preventing future bugs with regression tests.
So, we've solved the current cases, which is great. But as we all know, old bugs have a really nasty habit of coming back from the dead. And that brings us to the regression test. A regression test is simply a permanent automated check that you add to your testing suite, and it runs every single time you update your codebase. And this brilliantly illustrates our whole detective analogy. If debugging is like catching the thief, writing a regression test is exactly like installing a permanent security camera pointing right at the window they broke in through. If anyone or anything ever tries to break that specific window again, alarms will instantly go off.
So you fixed the bug, but how do you know your foundation is truly bulletproof? Well, the answer is you trust your regression tests and your debug reports. By systematically reproducing, isolating, fixing, and verifying every single flaw, we've officially transformed our fragile little sandbox into a hardened, secure component. We are now completely ready to assemble our final capstone project in the next lesson without dragging any of these old bugs along with us. I really hope this explainer gave you a powerful framework for tackling your own smart contract mysteries. Remember to visit forge.college to dive deeper into this subject and discover even more Web3 content. Until next time, keep questioning the strength of your code and happy debugging.